Morning, guys. So I hope you guys have understood the portions which we have taken in the live class, because the video which I'm going to take is a continuation of it, right? So work energy power, as you have must have heard, is included in your examination. That's why this video which you are seeing now will be of 1.5 hours, right? I'm extremely sorry, guys. We have to finish it because we are behind time, right? But don't worry, I will be including all the topics, both NEET as well as what your school portions wise. Okay, so starting with the simple topic, which is you have completely or understood kinetic energy, right? So today, or the first section which we are going to have, is potential energy. Clear? Right. So what do you mean by potential energy, right? What is the layman thing which you have learned in your 9th or 10th class? It is the energy which is stored in the body, right? Or the energy which is there in the body due to its position is known as potential energy, right? And you would have learned that it is quite its magnitude is what, mgh. That also would have been taught to you guys, right? So similarly, I am just telling it again. What do you mean by kinetic energy? Energy which is there in a body due to its motion, right? So this and all is common thing, but right. So suppose we consider a ball, right? Let us say that ball is away from the ground with a distance h from here, right? Let's say this is the ball, right? Let the mass of the ball be m. So there will be a weight downwards by this ball, which is mg, right? So that is the f, or the force which is acting here, is mg on the ball, right? So what is work done here? Work done is force into displacement, right? So when the ball falls from here, or even if it is not falling, right, let's say it is stained itself, so the force acting here is downward, right? And the displacement is actually what, h, right? So due to this position, a work done is done, right? This against this force, or against mg, a work done is done by this ball when it is just standing there, right? That force is mg, and the displacement against which it is working, right? Here, that is h. It is trying to remain here itself, right? So this is work done is equal to mgh. Clear? Right. Now, see, I just told you before that there is an energy actually is or I can say classified into two mainly: kinetic energy and potential energy. So we'll see what is the interconversion of kinetic energy and potential energy when a ball is falling or free fall, right? That is, let's say, same example, right? Initially the ball is here, right? Let's say it is at a height h from here, from the ground, right? So when the ball is released from this height h, right, it comes down with what? Increasing velocity. I'm not indicating positive velocity, I'm it's showing that the velocity is increasing while the ball falls, right? But what was the initial velocity? It was 0, right? So here I can write v squared is equal to u squared plus 2gh, right? Why 2g? G is the acceleration here, h is the displacement which is going to, or how much traveling the ball is going to do. So v squared is equal to u is 0, then 2gh, or I can just write here, right, v squared, let it remain there itself, means this much velocity, right? This much velocity, v squared by 2gh, is a final velocity when the ball reaches the lower position. Now let's say there is a point here just before the ball strikes the ground. That is, at that point, what will be the kinetic energy? Kinetic energy will be half mv square, right? Substitute for this v square from here, it becomes half m2 into gh, right? Now can I cancel 2? Yes, you will get mgh, right? That is, remember in this scenario, right, when the ball was in here, right, it had what energy? Potential energy, which was equal to mgh. just while the ball was trying or moving or fall down, and just before it strikes the ground, it is having kinetic energy, which is magnitude, not the equation, its magnitude is also mgh. So I can say when the ball is freely falling, the energy is remaining constant, right? That is, I can change the stored potential energy was completely converted into kinetic energy just before the ball reaches the ground. Clear? This is something you have learned in your lower classes. We are just brushing up, because before you understand this concept, I don't believe it is better to go for the next complicated topics. Clear? Right. Now this comes, which is new for you guys, right? So when you look into the books like H.C. Verma, right, and other technical books, means the books which are we are going to deal with Dinesh also, that is NEET oriented books here, and those books, actually it is not the potential energy which is defined. As it is, potential energy is not defined. The quantity which is defined or mentioned is change in potential energy. Change in potential energy, and potential energy is usually indicated by U. So change in potential is delta U, right? And there it is mentioned that change in potential energy is equal to minus of work done by conservative force. Keep in mind, it should be conservative force, right? Sorry for the sound which came up. Let me make it silent. Okay, so what is change in potential energy? It is equal to negative work done by the conservative force, right? Neta U, that is change in potential energy, is not defined for non-conservative force. Keep that in mind, right? Only for conservative force. Clear? Potential rate change in potential energy is only for conservative force. Clear? This work done, how much work done is done by a conservative force, is actually stored into, or is usually used for changing the potential energy. That is its meaning. I am telling you again. See, when you suppose this is ouch, this is the initial position of ball. You're doing some work and you're bringing the ball to another position, say like this, right? So that means you are doing some work, right? That work is done to move a ball from a higher potential energy to lower potential energy. So this change in potential energy was brought up by W, right? So that's why change in potential energy, delta U, is actually final potential energy minus initial potential energy is equal to minus WC. Why did I write minus WC? Work done by work done by conservative force, that's indicated by WC. Clear? These are all our theory, guys. Clear? So suppose here, let's say two levels we are going to, let's say this is your ground, right? There is a level here and another level here, right? Let's say there is a mass M here, right? And I am going to bring it above here, right? That is, let's say this mass is at a height h1 from ground, and this mass is a height h2 from ground. Clear? And what will be this height? It will be h2 minus h1. Common sense, right? Clear? We are going to explain that whether it is true or not. We just told that this change in potential energy is negative work done by the conservative force. We are going to prove this one. Okay. Now this much explanation is not there in your textbook, but I believe that it is better to make you guys understand the theory concept properly, right? Now what I am going to do, let's make some points. This is A position and this is B position. I am going to bring the mass M from A to B like this. Okay. Now we know what will be the final here. Final potential energy mgh2, right? What will be initial potential energy? mgh1. right? What will be UF minus UI, final minus initial potential energy? Mg is common there, right? So H2 minus H1, right? Clear? Keep it there itself. Right, now let's deal what is we just want to prove that UF minus UI is equal to minus WC, right? So let's see what is WC, that is work done by a conservative force, right? And what is that conservative force which is doing the work? It is weight, na? Mg is the one which is doing the conservative. Oh, I rubbed off, right? So let's say this is Mg, right? And Mg is in this direction, right? What is the displacement of M? H2 minus H1, right? The mass is displacing by this much height, and this is a force acting against that, right? So I will write WC is equal to, right? What? See, tell me the direction. Displacement in this direction, force in this direction, that is the angle between them is 180 degrees. So negative work done minus mg, force, into displacement is H2 minus H1, right? So let's take this one as minus WC, so this becomes mg H2 minus H1, right? And there is here another equation. Compare these two equations, which is having its RHS side equal. So I can write UF minus UI is equal to minus WC. Hence proved, right? That is change in potential energy is equal to negative of conservative work done, right? Or work done by a conservative force. Simple, right? Clear? Or you can just write less like the as the previous section we wrote, you just can write delta U is equal to minus WC. You remember delta KE is equal to WC. Remember? Change in work energy theorem we discussed in the live class, right? Clear? Why it became like this? It's a common sense, guys. See, initially the ball was, let's say like this. I will tell with the example of ball. Initially the ball was at the high position, let's say. It was having higher what? Potential energy, right? Right. So as it goes down, the potential energy goes on decreasing and the kinetic energy increases such that at just below the striking the ground, kinetic energy will be maximum and potential energy will be zero. Just to zero or the minimum value. Right? So I can say that kinetic energy is equal to what? Negative of potential energy. Both are in opposite nature. When one is high, the other is low, like that. Clear? Or you can even explain it in another way. You know, kinetic energy plus potential energy is total energy or total mechanical energy, right? Here let's put delta, here also delta, and here delta, right? Clear? And during a system, this is an entire system, right? So the total energy, right, entire system is, let's say, is 0, right? So I can say delta KE plus delta PE will be equal to 0, or delta KE is equal to minus delta PE. You can even explain this way, right? So kinetic energy is equal to negative, or rate change in kinetic energy is equal to negative potential energy. Clear? Right? Why, if you guys are having doubt why did I write delta T is equal to 0, it's a simple concept because I just come up and I think you guys might not be catching it. See, total energy for a system is always constant. Remember that, right? That is something you have learned in your lower class. Total energy of any system will be constant. If something is constant, then there cannot be any change. That's why I wrote delta change in total energy is 0, because it is always constant. So there will not be any change, right? That's why we equated it is to 0. If not, if you didn't understand, better you understand now. Clear? Right. So we just wrote change in potential energy is equal to minus of work done by conservative force, right? Suppose this change is very small, then you can replace delta with du is equal to, this becomes dwc. You can do it also, nothing wrong with it, right? Someone asks you what is the relationship between what change in potential energy, that is, you are asked what is the relationship between change in potential energy, right? Change in potential energy and your and with the force, right, or conservative force. How would you write? Very easy, you can go for this one. See, this delta u, right, if I am asked, or if you guys are asked for a small potential energy, you will write it as du, then this becomes wc will become minus dwc, right? Now what is dwc, or what is very small work done, is equal to force into, for a small displacement, right? So here I can write minus f dx, right? Right, so here I can write for du is equal to minus f dx, or I can write f is equal to minus du by dx. This is a relationship between force and change in potential energy, right? Clear? That is, small change in potential energy with respect to small change in displacement gives you force. Clear? This much is clear, right? Right, I'm blinking all the topics, guys, right? So when you look into the graph, or sorry, here this x is coming here, right? X means the displacement is in x direction, so here you are mandatory to write for fx, because for force, conservative force in y direction will be minus du by dy, because the displacement will be in y direction. Similarly for z, keep this in mind. Clear? Right? Now moving on, so we just wrote fx is equal to minus du by dx, right? Now I hope you remember, for any xy graph, right, for any xy graph, dy by dx indicates slope. Remember, for any xi graph, dy by dx will be indicating slope. That is, if this is x and this is y, then this slope is dy by dx, right? Clear? That's how you take, right? For instantaneous value, etc., you have done. If you don't remember, right, this is t, this is s, displacement, slope, ds by dt, that is your velocity. Anything which is in y direction, that is s ds, divided by x direction variable dt, right? This and all you have to remember. It's not something which you are hearing for the first time, right? So similarly, look into the previous equation of fx, which is du and dx, right? So if you have a graph between potential energy and displacement, the slopes, right, the slope of the graph gives you fx, but it will give you fx negative value, right, because you are finding minus du by dx. Or if you have the problem, we will write du by dx is equal to minus fx. That's better, right? So slope is giving you minus fx. You can take that one, right? Slope of a ux graph, that is potential energy and displacement graphs, slope gives you conservative force in negative value. Clear? Right? Now this and all will come in a combined form. This and all are some theory sections which are going on. Clear? This much is clear, right? Now the same equation, guys, we had du is equal to, remember, f minus fc dx. Why I am writing c is just to make sure that it is conservative force, you understand it. Alright, so for a larger section, this is for, suppose this is for a potential energy for a small area, right? Suppose you are asked for a larger area, so you would have to integrate, right? Initial potential energy to final potential energy, du is equal to minus integral x1 to x2 f dx. right? The problems can come in this way. I'll tell you where it will come. This much is clear, right? Hope this much is clear, right? So what and all we learned? We learned what is the relationship between potential energy and work is equal to minus work done, right? And we proved this statement. Then we talked about a little. We learned about a little bit about potential energy. What is its equation? What is its relationship between kinetic energy? How the conservation is happening? And we later on we go over this equation. And after this equation was done, we also talked how potential energy is equal to, right, change in potential energy is equal to minus change in kinetic energy. We talked about that. Then we talked about what? I believe we talked about what is the relationship between potential energy and force, right? We found an equation and we found that potential energy and displacement's graph slope will be giving negative force value, right? This and all other things we covered till now, and we just found using just small variable of potential energy, you can even find the entire potential energy by integrating both the sides. Clear? Right? Now suppose a question is given like this, right? That is F is equal to 2x is given, right? It's a conservative or conserved force. You are given U at x is equal to 1, that is the initial position is 10 joules, right? That is potential energy at x is equal to 1 is 10 joules. You are asked what is the potential energy at x is equal to 2, right? This is the type of a question here. You will have no idea if you don't have any understanding about relationship between potential energy and force, right? So we'll start with the basic, then I'll tell you the what for go for what anyways, let's go. Let me say whether this force is constant or variable. This is a variable force, right? Remember, this is a variable force, right? So delta U, right, is equal to, right, minus W. See, right? Or in place of delta U, you can write it as UF minus UI is equal to minus WC, right? Here it is what? 2 is the final one. So U2 minus 1 is the position 1 is equal to minus WC. Right? In place of WC, right, when say work done, total work done by a variable force is integral F dot dx, right? Right? It's just like the previous one here, right? So here I'm going to write in place of WC, I will write integral F dot dx, F dot dx. But when from where to where? From x1 to x2. Right, and here x1 is how much? 1, and how much is x2? 2, right? Clear? Right, this is u2 minus u1, right? Now what is u1 given as? U1 is given as 10, so u2 minus 10 is equal to this value, right? So now I can just replace f with what? 2x, right, dx, that is what is given in the question, right? Right, and here u2 minus 10. Now integrate this one. 2 is constant, right? Integrating x, it is x squared by 2. Upper limit, lower limit. Then 2 cancels out. Put the upper limit here, so it becomes 2 squared minus lower limit here 1 squared, right? That 2 squared minus 1 squared is 3. 4 minus 1 is 3. So I can write u2. Oh, there is a minus, no? I'm sorry. That's why the entire calculation become wrong, right? There is a minus here. There is a minus here. So here also there is a minus, right? So here also there is a minus in outside bracket. So this becomes as minus 3. So u2 minus 10 is equal to minus 3, or u2 is equal to plus 7 joules. I hope you understand that joule is the unit of energy, potential energy or kinetic energy whatsoever. Clear? You got an answer, right? Now suppose the question is changed, right? You are given the conservative force is given as 3I plus 4j cap, right? And you are given that potential energy at 0, 1 is equal to 10 joules, and potential energy at 2 3 is equal to what? That is your question. This much only will be given, guys. So how would you solve it? So here, see, you are given fx here and you are given fy. Remember, see, any vector a can be written as ax I cap plus ay j cap. Remember, so here ax is this one, ay is this one, if this term had been a. So this is fc now. So this fc or f actually can be written as fx I cap plus fy j cap. So comparing these two terms, 3 is fx, 4 is fy. Keep that in mind. Okay, right? So just like the previous case, change in potential energy is equal to minus work done by the conservative force minus, in place of wc, right? This force is a variable force, a variation force, or variable force. I will write it as integral f dot dx, right? F dot dx, I just told you, remember, is actually fx into dx, that is force in x direction, plus integral fy dy, right? Clear? I have not put the limit, we'll go to that. This much clear? But why did I split here? Because you are having force in two terms, so two variables has to be written, right? Force into displacement in x direction, force into displacement in y direction. Clear? From where to where? X is changing from 0 to 2, so 0 to 2. Y is changing from 0 to 3, 0 to 3, 1 to 3, sorry, 1 to 3, right? Clear? Now put the values here. In the values in these equations, it is equal to minus integral 0 to 2 fx is 3 dx plus integral 1 to 3, right? Fy is 4 dy, right? Now that is equal to minus integral 3 dx, 3 is constant, then integral dx. Integral dx is x, right? This is 2, this is 1, plus 4, right? Let's take that as constant. Now 4 is constant. Integral dy is y, upper limit 3, lower limit 1, right? So this becomes what? Minus 3, right? This is 2 minus 0, that is 2, plus 4, 3 minus 1 is 2, right? So you will get 6 plus 8, that is 14, or it is minus 14 joules, right? That is not finished. What is the LHS side? It was UF minus initial is 10 joules, right? So it is 10. So UF, you will get it as minus 4 joules. You got the answer? Clear? Right? Now, there is a thing which is not mentioned in your textbook, but I want to make sure you understand. See, you write mgh for potential energy now, when it is at a position from ground, etc. This potential energy is due to gravitation, right? So actually this potential energy is actually gravitational potential. There is another equation for that also. If you study in what you will study later on, that it is actually minus gm by r in gravitation chapter, where g is acceleration, gravitational constant, m is the mass of earth, small m is the body where it is placed, and r is the distance between them. So potential energy difference between the small mass and earth, which is having mass, is this equation. You will learn later on, right? So there also you will derive there is a relation with this equation also. So I'm just making sure you understand, right? This is actually known as gravitational potential energy because it's provided by earth, right? Suppose you are having a body like this continuously, and it is at a height h from ground. Obviously you know the potential energy equation is this one. Now what happens if you are having the same body arranged in this fashion? What will the change in or what will the potential energy here? It is not, see, not as a continuous form, okay? That is, I'm telling you, it is as a chain, right? So actually most of the mass will be centered at its center. That's why you're supposed that also you will learn, that is known as center of mass in the next chapter, I believe, right? So the mass is concentrated at half the height from the ground. That's why usually it is U mg h by 2. Just understand it. I will take it later on, right? Suppose there is a ground and the body is lying like this, right? Then obviously the potential energy will be zero. This is something you know, not a big deal thing. Clear? Right. Now this and all are not mentioned in your textbook, but it's just good to know things. Clear? So before going to the spring section, there is a small problem I want you guys to do. If your theory is strong, or no, I don't think it will be able to, you guys will be able to solve it, because it's a little bit tougher one, right? It's a semicircle and a body is arranged like this. Let's say it is a chain or whatsoever, right? It is not straightly arranged. Let's say this this semicircle is having a radius, let's say r, right? Clear? And obviously you are asked what is the potential energy. So let's say this entire chain is having mass m, and acceleration due to gravity g is given, right? So you are asked what is the potential energy of this chain or body which is aligned in this form. How would you do it? So this is an entire process. So I'm going to rub off this mass. For this type, remember this thing step by step, right? See, if it had been a constant body, we found u is equal to mgh etc etc. But if this an alignment is there, it is very difficult. So better if you are able to take any part of it. Remember, if you are not able to find the entire area, what did I say? Just find a small area dx, then multiply it, right? Then you will get the total area. Multiply, or I said integrate it from one end to other. The same process we have to do here also, right? Suppose I consider a small part from here. This is not there in your textbook, but it has been asked in your examination, right? That's why I'm telling you, right? So let's say this dm mass is making an angle d theta with the center of the circle, right? Now let's say this angle is theta also. Just mark it like this, right? Now du, that is the potential energy of this small part, will be, I can say this is at a height, let's say h distance, right? This one, h distance, right? Okay, that is du will be dm, right? This much is having mass only dm g h is the height from here, right? Now let's say what will be this height, guys? This is r, right? So this will be r sine theta, this will be r sine theta, right? Vertical component, right? So du is equal to dmg r sine theta, right? This much clear, right? If you want to find the entire potential energy, you have to integrate it. So integrating one side means integrating the other side, right? From where to where you want? From here to here, that is 0 to 90 degrees, 0 to 90 degree. Integral du will be u, right? So need not write it, right? Clear? Not finished, guys, right? So how would you solve this type of constant problem? See, in this derivation or integral part, theta is there, but nothing of the term here. See, dm is there. One is, there is a angle section that is sine theta, and the other term is mass differential form. So it is difficult, right? So we have to arrange the entire thing in a common form, right? So this is the same arc. You look at this one, arc dm, right? And it is subtending an angle d theta, and this radius is r, right? So can't I write here d theta, or I can say dm, that is arc length. Dm is equal to radius into the angle subtended by the arc, that is d theta, right? Clear? This is not something which is additionally added. This is a very good question, guys. And this is a purely application based question, right? Now, what is the entire area of the semicircle? Not area, circumference. It is semicircle, right? So it will be pi r, right? And out of this also only half of it is there. So what is the circumference here? pi r2. So this entire chain, right, is covering a length of pi r2, right? And I am telling this entire length is having mass m, right? That is pi r by 2, its mass is m. So 1 unit will be having how much mass? M divided by pi r by 2, right? So how much length mass do I want? I want the arc length. How much? I want the arc length of this much is the arc length, right? DMs. Oh, sorry, it ran off, right? Remember, we found the DM's value, the mass. This DM is arc length is equal to r into d theta. This DM mass, this much portions arc length is r d theta, right? Clear? So similarly, right, so 1 unit's mass is this much, means how much will be the mass of that much portion? That is r d theta portion. It will be mass of 1 unit into r d theta, that is my m divided by pi r by 2 into r d theta. This much clear, right? You can cancel a lot of things. R and R can be cancelled. 2 goes up, right? So you can write now the small chain section, this much dm mass object, right, has having a or mass is what? This mass of the small portion dm is equal to 2m d theta by pi, right? Now let's come back to the initial equation, this one, that is integral du, that is actually u, na? So u is equal to integral 0 to 90 degree. What is dm now? What is dm now? We just found dm as 2m by pi d theta, right? And there is r, then sine theta, right? Now all the terms are in theta form. Now it is easy to integrate. Now let's move on by removing constant terms. Removing means bringing it out. 2m by pi constant, r is constant, 0 to 90 degree, right? And there is a sine theta d theta. Now what is integral sine theta d theta? It is minus cos theta. 2m r by pi minus cos theta, upper limit 90 degree, lower limit 0 degree. Now substitute the value. 2m r by pi minus cos 90 degree is minus 0, minus of 0 degree, minus of minus 1. No, minus 1. No. Yeah, clear, right? Or you want, you have can do this one. You put 0 or minus value here, minus cos theta, and you just write this one as cos theta. So cos 90 degree, so put here minus, right? Cos 90 degree is 0, right? Then minus 1, cos 1. So you will have only minus 1 here inside that, and there is a minus outside. So you can write 2m r by pi. See, you did a lot of section and you just found that the 2m potential energy of this quarter is 2m bar pi. Clear? So what will be the first entire thing? It will be mr by pi. See, it's very easy. So this section, if you want, you guys can by hearted. See, I think there is a loss. Okay. See. I'm sorry. There is a g left off here, na? So just add the g here. I'm sorry. The g is constant. We bring that outside. That's why I remembered the equation. So there is a g missing. So u is equal to 2mrg by pi. Clear? Now the next topic, which is actually a very big important topic, which is spring. Right? You have to learn this one in a detailed form. You have a little bit idea in the laws of motion, but this is something which you have to learn a lot. Right? So I hope you know spring. Right? You draw it like this. Right? Let's say this is body. Let's say this is joint at constant section. Right? When you pull it, right? So usually you apply a force, so the spring will have its own force which is against the applied force, which is known as spring force, and you learn that spring force is equal to minus kx, right? Where spring constant is k and x is the displacement, right? Remember, this is also called Hooke's law. Hooke's law, right? Right. So someone asks you to plot, and okay, something which I have to tell you in between is x, if you are extending or you are pulling, so this direction is positive, right? So x will be positive. If you are compressing the spring, then x is negative, because movement is in this direction positive, movement in this direction is negative. Keep that in mind, right? Clear? Right. Now if you are asked to plot this graph or this equation graphically, that is, what is the relation of graph for force of spring and displacement, how would you plot it? I would recommend that you guys pause the video and try to draw it by yourself. I hope you guys have plotted the graph after pausing the video. If not, look how I'm plotting. So this is your spring force, this is displacement, right? Keep that inside. Okay, let's write here. Now let's take two cases. First one, or three cases, let's say. Case one, right? When the initial, this is a spring and the block, right? It is at rest. No motion is happening in the case of the block. It is at rest. So I will say x is no displacement. So x is equal to 0. So Fs will be equal to 0, right? So the point will be here. Ish. I hope you understood what it is, right? Now put for the next case. Suppose I am what? Compressing the spring. That is the case 2. I'm going to compress, right? Compress means I can understand pictorially that this will be the position, right? So that means a force was applied in this direction, so the spring force will be in this direction, so x is also in this direction. Now that is the compression is happening, so x is in this direction, and I told you this direction is negative. So case 2, x is negative, right? And what is Fs? It is in this direction, so it is positive, right? Clear? Right? So let me do one thing. Shall bring here, right? Right. So initially it was here, right? This case 1, and case 2, that is when x is negative, that is here, then force is positive, that is spring force, right? So you will mark the point here. Sorry, right? Clear? Let's make it as a cross, then it is no problem, right? Clear? The next case, case 3, I'm going to take case 3, right? That is x will be what? That is c. I'm going to extend it back to its initial position itself, right? So that means I am pulling it in this direction. I'm applying force F, so spring force will be in this direction, that is Fs is negative. In the force direction itself, the displacement is happening, so x is positive and Fs is negative, right? So when I plot, see, x is positive here, then Fs is negative, means here. So let's say this is the point, right? It should be a straight line. It's supposed to look like a straight line, right? This is the force displacement graph of a spring. Clear? Right? Now similarly, we'll talk about work done by or in a spring. Who is doing the work? Work done by the spring force, right? Work done by spring force, right? That is, the string is stretched. That is what is not string, spring, right? Suppose the first condition, let's say the spring is stretched, right? That is, x will be positive, right? And Fs will be negative. We learned it previously, remember, right? So if you want, I can even show you pictorially. Let's say initial positions like this, the spring was like this and the body was here, right? Now here what I'm going to do is I'm going to stretch it like this, right? Clear? Let's say this position is x is equal to 0 and this position x is equal to xm. It's maximum position, right? So what is initial position? 0. I have extended to xm, right? So what is work's equation? Work is equal to, for a variable force, right, integral x1, that is xi, to xf, final position, Fs ds. What is Fs? Force exerted by the spring, right? And here I can write W is equal to integral x is equal to 0, that is initial position, and it is stretched to maximum position of xm minus kx, right? Fs is minus kx dx, right? So I can write k as constant outside, so it is minus k integral x to 0 x equal to 0 to xm x dx, right? Or I can write it as minus k x squared by 2 xm from 0 to xm, right? 0th value, right? That is equal to minus k, right? Xm value for the upper limit, that is xm squared, then lower limit becomes 0, so you need not write. So you will get the value as minus kxm squared by 2. That is the work done by a spring, right, when it is being stretched. Work done during stretching, that is minus kxm squared by 2, right? Similarly, let's talk about if it is compressed back to its initial position. Right, that is the displacement is from xm to x is equal to 0, right? That is I'm going to compress, right? So when the spring is compressed, we know x is this in this direction now, so x is negative, so against that the spring force is acting, that is Fs is positive. That keep that in mind, right? So work done is equal to, again, initial position is x is equal to xm, so I will just write it as xm here, xm to final position 0, right, Fs dx, right? That is equal to, now the calculation is same, xm to 0, right? I need not do the integration now, I will just put the values here. You will get the integration term as, let's put minus k outside, so minus k, right? So x squared by 2, right, upper limit, lower limit, put upper limit becomes 0, minus xm squared, right? So minus k minus xm squared by 2, upper limit value minus lower limit value, right? So minus minus goes off, right? So it becomes plus. So I can say now it is while you are compressing compressing the spring, you are getting the value plus k xm squared by 2. While stretching, this is compressing, while stretching it was minus kx squared by 2, right? So when you are compressing, right, the energy is getting stored. Remember I told you, when work is positive, you are giving the energy to the body. When the work is negative, you are taking energy from the body, right? So when you are giving positive work, means that energy is stored in the body. When it is, that means when it is happening positive, when the spring is compressed. Clear? Keep that in mind, right? Clear? Right. So if someone asks, okay, I will write the, for general formula also it's required, right? So that means the same scenario, let's say the spring is here, this is the initial mean position. Let's say it is stretched from this mean position to x1, right? Again, let's say it can be even stretched to another position x2. Or better, I can say, let's say this is not the initial position. I will say this is a better one. Let's say we are going to take this as origin, right? And let's say the block is here itself initially, right? So this becomes the origin, that is x1, that is initial position. and the block is now going to be moved here so that the new position becomes x2. So force, the same equation you are going to root for work now. Just remove the force, write it as work is equal to integral, initial position is x1 to x2 f dx, right? So in place of f you can write integral x1 to x2, in place of f you can write minus kx dx. The same integration can be done, so it will be minus k x squared by 2, right? Upper limit, lower limit, right? Now put the upper limit, my lower limit value. So minus k x2 squared by 2 minus x1 squared by 2. Or you can write the general formula for work done by a spring force is equal to minus 1 by 2k, right? x2 squared minus x1 squared. Simple, right? Clear? Right. Now similarly, remember we had a relationship for potential energy, right? If you are asked what is the potential energy of the spring, right? This work is done on the spring, right? And that work is stored as potential energy in the spring. If you are asked what is the potential energy in spring, see, remember I have told you that change in potential energy is equal to minus work done by the conservative force. This is a conservative force. So in here, by looking at the previous equation, I can write delta U is equal to what? Minus of minus. This minus goes off, so it becomes half k x2 squared minus x1 squared. Right? Clear? Right. So this is the equation while doing or moving a spring from its initial position to final position. This is the change in potential energy. See, only the minus value changes. Potential energy is positive, work energy is negative. Clear? No, finished. Suppose, right, just like the previous case, I am going to say the initial position is x is equal to 0. So this term goes as 0. So I can write a general, then u2. Okay, if you I can make a simple change for you guys to get a proper equation for potential energy. So that is, here we have got a proper equation, that is I can write delta U is equal to half k x2 squared minus half k x1 squared. I just split it up, right? So that means suppose the spring was in its natural way. Natural way means nothing has been happened. That means I can say initially its potential energy was 0 at that place, right? Nothing has been done. If you don't know, just understand why okay, potential energy is 0, because I will tell that in detail. Just now know about this one. I will tell you why the potential energy is 0 just coming up, right? Just keep this one in mind, that initially when the spring is at rest, right, its potential energy is at 0. Keep that in mind, right? Why I will tell you later on. I will tell you guys, don't worry. Right, so this condition I am going to do when it is, suppose the body is at its natural form, or I can say mean position. So this x1 becomes 0, mean position. So potential energy becomes 0 there, right? That is u1 becomes 0. So this is u2 minus u1. So this term will have only u2, and this term goes off, x1 goes off. So it can write half k x2 squared. So generally I can write potential energy is equal to half k x squared, right? Work done, remember, is equal to half k x1 squared minus half k x2 squared. First I wrote this minus and then plus. It's okay if you arrange this way also, it's not wrong, right? This is potential energy at a point. Change in potential energy is what? Half k x2 squared minus half k x1 squared. Look into the equation, you will understand what I have done. This and all are equations you have to mug up, no other way. Clear? Now I told you, I tell you why the mean position or the resting position, the potential energy is 0. I will tell you, I told you now. So that's because we'll do that with a simple example. Right, that is where they are talking about conservation of mechanical energy in the case of spring. Suppose this is a spring, guys, right? Suppose it can be stretched to maximum position xm, it can be stretched to minus xm in this position. This is the origin where the position is 0, the simpler one, right? So in this position, guys, when you bring this one to maximum and then you leave, this block will be moving to and fro now, right? So it will be moving about the mean position, that it has a tendency to move in this forward and backward direction, right? It can have higher velocity. It has a, see, just like this one, you are having a ball, you are trying to throw it, so you are having a velocity, right? Similarly, this is the mean position, just like the ground position of your ball, right? So it has a tendency to have velocity change, right? That's why I told that the mean position has how much velocity? It has the maximum velocity, right? And remember, we told that when the ball reaches the maximum point, its velocity is 0. Similarly, if this is, I'm just drawing the mean position, this is a resting position of your spring. When it moves to the maximum position here, its velocity becomes 0. Similarly, when it moves to this maximum position, here also the velocity is 0. And velocity is maximum where? At its mean position. Keep this in mind. Clear? Clear. Can you tell me from where to where and all will be the potentially energy high, where will be the potentially energy minimum? So this is, let's say, line which I have arranged. This is the mean position of the spring, that is, the block has not moved, still it is at rest, right? I told you that at this position the velocity is maximum, right? And velocity is actually 0 here, and velocity is 0. I hope you understood why. Just like you are throwing a ball, man, here it's a resting, just throwing, right? Just like that, the block has, or due to spring motion, the block has a tendency to move in the either side, right? So in that position the velocity is maximum, right? So tell me here, velocity maximum means what will be maximum here? Kinetic energy will be maximum, right? So when the spring is at rest, means it has just moving, it has a tendency to move in to and from motion. At that point, at its mean position, that is x is equal to 0 condition, it is having highest kinetic energy. So in this point will be here having potential energy, what? Maximum. Keep that in mind, because its position is high, just like that one. When the block is at higher position, its velocity is 0, right? So kinetic energy will be equal to 0. Velocity is 0, maximum position. Similarly, here potential energy will be 0, because no position change, potential energy is 0. Similarly, in this condition, the kinetic energy will be 0, right? Or you can write, okay, all right, and the potential energy will be what? Maximum. If you want, we can arrange it in a beautiful way. The same thing we are going to write, but I just want to make it look good, right? So let's write potential energy maximum, kinetic energy 0, right? Here potential energy 0, kinetic energy maximum. Clear? Right? This can be even pictorially represented by a graph that we'll take in the next class. Similarly, a concept or a question, because I really like doing numerical questions, that's why. Suppose there is a spring like this and a block of M here, right? And spring is having a spring constant K, so obviously there will be a weight downwards, right? So after some time there will be an extraction, right? The spring will be stretched out, right? So let's say the mass is in this direction, so mg will be in this direction now, right? Suppose the displacement, right, or of the spring, or the stretching of the spring is by x distance. This is the natural condition, this is the stretched out condition, right? So there will be a spring force, right, Fs, which is equal to kx. I'm writing positive because I have already drawn direction which is opposite, that's why. This is force, this is spring force, right? Now you know spring force kx. Suppose see, once it falls off, or the spring has stretched out, now it is in equilibrium position, right? So at equilibrium position I can say spring force is equal to weight mg, right? So spring force I can write kx is equal to mg, right? Or I can write x is equal to mg by k. right? Now what is the potential energy of the spring? We have written it as U is equal to half kx square, general equation for any position, right? So that is half k, in place of x I will write mg by k whole square, right? So you will get U is equal to half, there is a k, right? There is k squared, now there is a k, so you can cancel that also, right? So half mg m squared g squared by k, that is the expression for potential energy. Now sometimes in the same scenario picture, right, sometimes the position of the mass with respect to ground is given, then the thing goes off. Clear? Right, I hope this much is clear. Right, if at all, okay, I will write that also. If at all you are given the position of the stretched off block is at a distance h from the ground, then that gravitational potential energy of mgh has to be also included here, like this. So the total answer will become like this. Clear?